So now we have to click on this folder icon and we will enter into that folder. We'll find all the relevant files over here, the data file, the models file, results file, also uh, the three folders: data, models, and results, and also other files, the classification.py, environment linux.yml, environment windows.yml, then lung cancer model H5 file, readme file, sample preprocessing.py file, and train.py file. So readme file describes how these files are organized. So under the data file we have different files for that Luna 16 dataset. So it has been divided in train, validation, and test dataset. Also the models I have already trained, and these are the some results that I have found. So how to set up the environment, it has been described over here. So in the Anaconda prompt we have to uh, run the command. So the Anaconda prompt, we are selecting the Anaconda prompt, then we will change the directory to that folder that has been selected. Then after that it says the readme file says that I have to set the environment by writing this command in the command prompt. So before that I need to see whether the environments are already listed. So I can see that this environment file is already listed. So for showing that how that environment can be set up in that in this Windows environment, we need to remove that that environment first. For this one we need to run this command. It will remove the existing environment. So it will take some time. So it has removed the existing environment. To see whether the environment is present or not, or correctly removed, we need to check the environments again. So you can see that that environment is not there, so it's already removed. So now I will run that command from the readme file. For the Windows we need to write this one. So it will download and install all the packages from the environment. It's collecting the environment. It will take some time. So you can see that environment has been installed properly. Now we need to activate this environment by writing conda activate the environment name. So we can actually copy paste from here. So if we just paste here, so it's not okay. So it has activated the environment. So now we can actually run that classification.py file, but by running this command. that will do the classification with already trained model. So it is asking for the data directory. So in the data directory, I just need to set the path here. So to setting the path, it will load that trained model, give the information about it, and it will be working on the classification using the trained model first. So this is a CNN model. So this is the classification. It will be showing the classification performance, and this is the confusion matrix. So we can see that around 1304 has been correctly classified as benign, and 240 are correctly classified as malignant. There are some false there are some false positive, and there are some false negative. So this is the confusion matrix. This gives the precision recall and F1 score for the trained model. So the performance is pretty good. Around there are 95% accuracy using that deep CNN model. Now it will give the classification result using SVM. It says that the training accuracy of the SVM classifier was around 98%, and the testing accuracy was 95.8076%, and the validation accuracy was around 95.9136%. So it's a very good performance, and the extractor feature was used using that deep CNN model. So using the XGBoost classifier, we have found the classification accuracy on the training dataset was around 99.94, that is around 100%, and the validation accuracy was 95.6823%, and for the testing accuracy using this XGBoost classifier was around 95.3144%. For the random forest classifier, the training accuracy was 100%, the validation accuracy was 95.7594%, and the testing accuracy was 95.3761%. That is pretty good. This classifier is performing pretty good. So this classification, now it is calculating the classification performance for the k nearest neighbor. So it is finding the best k value within the range from 1 to 25. So it will take some time. So same time, because it is through looping within the range of 1 to 25 to finding the best k value, which is giving the best validation accuracy, and it is the k value is 23, and the training accuracy was 97.76%, validation accuracy was 96.0678%, and testing accuracy was 95.1295%. So the code ran successfully, and we have seen that the best performance was obtained by using is VM classifier using the extracted feature with the deep CNN model. So for the prediction and the feature extraction, we have used that deep CNN model we have developed. Deep CNN model I have developed, and here we have just compared. I have compared the performance of different classifier, that is with that extracted feature, that is the support vector machine, XGBoost classifier, random forest, and KNN. And among these classifiers, I have found that SVM performed the best compared to others. So thank you. This is the this was the demonstration for the classification.py. For the sample preprocessing, we need to just write the command python sample preprocessing.py. If we want to retrain the model, we can do that by running it is asking for the sample data directory. So this was the data directory, we are setting that. So as I was saying that if we want to retrain the model, we will just simply run the code python train.py. So now it is showing the some sample image pre-processing for segmentation or something. So it is asking for the image number on which we need to apply that pre-processing technique. So let's see, we'll be searching for the result for image ID 100. So this is the sample image and this is the downsample image. So to clarify, this image is the segmented image from that Luna dataset. So in their website there are already a zip file that contain all the segmented portions of the um, lungs that had the nodules that gives the idea about benign and malignant uh, lung segments. So this is the sample image, this is the downsampled image, this is the upsampled version of that image. This gives the mean subtracted image, and this is the sample image, and this is the image after contrast enhancement. This gives some idea about the contrast and without contrast enhancement. This is the with contrast enhancements version of that segmented portion, and I have applied the BISC algorithm, which shows that this is one kind of key point detection technique. So it is showing that with the features, this kind of key point detector techniques, it shows the features that are important for the decision of benign and malignant. So another algorithm is Harris corner detection. So it is detecting the corners that are highly susceptible. This is a shift feature extractor feature detection technique, and this is the result after first key point detection technique, which is showing those edges that contain information about the feature, and it gives the ORB feature, that is oriented and rotated brief. So these are the all image processing technique. Now I will be running that train.py for retrain that model, but it will take some time. Actually, you can ask for the data directory. Yes, so it's asking for the data directory. So before that, actually we can set any type of number of epochs for which we want to run the train.py. For simplification, for now, as you can see, for simplification we will just run for 10 epoch instead of 100 epoch. It's just for the to see within a very short period of time, because as much we increase the time, increase the number of epochs, it will take much time for the training purpose. For the demonstration purpose, we will just show for 10 epochs now, but we can use 100, 200 to 500. So we have found better result for around 500 epochs. So we haven't set the data directory well, so we need to set again. So we are clearing that screen. So the data directory is this one. So let me run that file again, Python. So now I will run Python train.py. So it will ask for the data directory. For now, I will train for 10 epochs so that it will take less time. The more the epoch, the higher the time, and for around 500 epoch the train model performed pretty well. So this is the data directory, and it is giving some results for primary preprocessing. So this is the loaded model. It has started training. So it will take some time, and it will show the time, the loss and accuracy. This is the batch size. So if you use GPU for that, it will be much more faster. So you have seen that the validation accuracy was 82.58%. The learning rate was 0.001 for both uh, for this whole training for the first epoch, and it will optimize the learning rate. Also, you can see that the loss for training set was 0.6161, accuracy was 79.54, and the validation accuracy was around 82.58. So it's now running the second epoch. So we can see that it is increasing the accuracy and also decreasing the loss. That is what we expected. That is what I expected. That is what we expect actually. So you can see that the validation accuracy has increased. Also the training accuracy was increased, and the loss is decreasing. That is expected. Different model. So we are almost at the end of training, and we're getting very kind of around 86 after 10 epochs, and if we increase the epoch number, we will be able to get more and more accuracy. So this is the results. So we can see that it hasn't uh, converged completely, but it is the downward trend is being found for the loss. So this green one is the training loss, this red one is the validation loss, and this blue one is the training accuracy, and the orange one is the validation accuracy. So these are increasing, we can see from here, and these loss curves are decreasing. So that is the trend, and it's kind of converging. So I will now show, so that code runs successfully in the machine. So now I will show the results for different epochs, for 100 epochs. And so this was the result. So it was around 95 or so, and this was the results. So it did really well. So if we see for 200 epochs, we can see better results with some spikes. If we see 300, yeah, it did very well. Now if we see if the 400, it will also show that it has been kind of saturated now. It's kind of flat after I might say that for the validation loss it has been flat after 100 epoch, and for the training loss you can see it's being converged, and this is the result for the 500 epoch. There are some spikes over here for the loss of validation. So this is the final confusion matrix after 500 epoch. So there are some 36 false positive, so false negative. There is the true negative. This is the true positives value. So this is the result, and this is really good. And these are the results for different, for image 100. There are some image processing results. This is the output from the brisk algorithm. This is the contrast band. This is the Harris corner detection downsample image. The results after first key point detection. This is after mean subtracted. This is after ORB. After SIP.